Okay. Hello, everyone. So thanks for being here, and a big thank you to the organizers for giving me the opportunity to present this work here. Yeah, so this is a very vague working title because it's still very much a work in progress that I've been doing with Ben Withers. Yeah, but I think it's the most exciting project that I'm involved in, so I'm happy to present it here. Okay, so I want, yeah, in this work, I want to basically uncover some structures and shed some light on holographic prescriptions for Schwinger-Keldysh effective field theories, as the title suggests. So, why are we interested in this? We all know a lot about classical hydrodynamics, and it is still very useful, a very active area of research. But there are certain limitations in the classical formulations. The main one is that the classical formulation is at the level of the equations of motion. And it's generally very hard to write actions for dissipative systems. And also beyond linear response, it's not always very clear how to systematically include interactions, higher loop effects, interactions between the hydrodynamic modes with a thermal bath, which lead to these the so-called long time tails and stochastic effects in hydrodynamics. Also, it's not it's kind of not very obvious how to have direct access to the advanced symmetric Green's functions and other higher point time order correlators, which we would like to have also for experimental reasons. And finally, we would like to have some more fundamental derivation of certain phenomenological restrictions that we put in our hydrodynamic theories. So all these obstacles actually, they are overcome using Schwinger-Keldysh constructions. So Schwinger-Keldysh, the Schwinger-Keldysh setup is actually a systematic way of describing non-equilibrium phenomena in quantum field theory. It can give an action principle for hydrodynamics based on the so-called Schwinger-Keldysh closed time path contour. And also it uncovers some fundamental symmetry principles which lead to systematic inclusion of interactions and fluctuations, and which imply the Onsager relations and the second law of thermodynamics, which we usually impose by hand after writing down the constitutive relations. Also, for example, it has been used to systematically incorporate certain aspects of locality, which are not always obvious when you have complex systems such as pinned superfluids. And finally, beyond linear response, there are certain stochastic coefficients which are invisible to classical constitutive relations, but they are there in the Schwinger-Keldysh setup. Okay, so there are very good reasons to work with actions for hydrodynamics. And now let us ask why we want to do holography with that. So, of course, as we all know, holography is very useful because it allows us to do explicit computations in strongly coupled models, which are not amenable with other techniques usually. So we can have analytic results, for example, in derivative expansions. We can find universal bounds for centered transport coefficients of hydrodynamics, for example, the shear to entropy, the shear to entropy ratio, certain diffusivities. And these bounds are conjectured to hold universally. Yes? You mean, okay, it can get corrected by higher derivative. Okay. Yeah. Yeah, with higher derivative connections. Okay, still, um, okay, these kind of violations, they are somehow under control within holographic models, but okay, I don't have much to say about that. Okay, but at least we can do explicit calculations and compute them explicitly, even if they are not universal. Okay, also in holography, we generally expect generic behavior. So everything that is allowed by the structure of hydrodynamics is expected to be there unless there is some hidden reason not to be. And for example, there have been in the past certain accidents that we uncovered by understanding hydrodynamics better. I'm thinking here about certain damping attenuation relations that exist in models of pseudo-spontaneous symmetry breaking. And of course, it's much easier to do numerics with gravity than strongly coupled quantum field theory. So the goal of this talk is to shed some light basically in the gravitational duals of Schwinger-Keldysh quantum field theories. Okay, this is somehow related also to the recent discussion about the role of complex saddles in quantum gravity and holography. But of course, I don't have anything to say about that. And yeah, so there have been certain proposals of how to find holographic duals of Schwinger-Keldysh path integrals, and we want to understand the relation between them. Just for illustration, I will just consider the dynamics of a scalar field. You can think of it in the context of hydrodynamics as the model A in the classification by Hohenberg and Halpering, which describes critical relaxation dynamics. So I will only consider the dissipative part. Yep. Yes. So I will take this just because it's simpler to do calculations, but all the other models and general hydrodynamic theories, I don't believe that they have more than technical. It's just technically harder to do calculations with that, but conceptually, I hope that it is clear what we want to argue. Good. So yes, and actually what we want to understand, yeah, as I said, is to uncover some symmetry structures and constraints of Schwinger-Keldysh effective field theories, which are relevant for hydrodynamics. Okay, so after these very general words, let me just introduce Schwinger-Keldysh techniques in non-equilibrium quantum field theory. Yes. To do what? Okay. Yes. Yes. So yeah. I will show you in detail, but there actually have been two different prescriptions of deriving Schwinger-Keldysh effective field theories. Okay. We want to understand. Yeah. Yeah. I will. Yes. Yeah. We want to understand basically why they give the same results and how they are related. Of course, we will only do a small step towards this big goal. Yes, but yeah, this is what I will talk about. Good, yeah, so I will not have any new proposal for Schwinger-Keldysh holography. No, no, two are enough, yeah. Okay, good. So, yeah, let me just introduce certain aspects of Schwinger-Keldysh quantum field theory such that we are all on the same page. So, as we know, for example, the time evolution of a general density matrix has to do with both forward and backwards time evolution. So, this U and U dagger. Okay, this leads basically to correlation functions in general density matrices, matrices rho node, which are of the form trace of U dagger A, U, and certain insertions of operators. So in order to do computations basically with non-equilibrium density matrices, we can complexify the time contours as shown in these pictures. And so the forwards in real-time contour corresponds to U, and the backwards corresponds to U dagger. At very late times, we patch together these contours, and this corresponds to the trace that we have on the right side there. So if we consider general initial density matrices, we have these in complex time contours, but the most interesting is to consider thermal density matrices, in which case we can represent e to the minus beta h with some imaginary time evolution, as shown in the right side of this picture. So we can get general endpoint path order correlators from path integrals of the form shown here. So here on the left side, I have the generating functional in terms of sources which are inserted on these complex time contours. Okay. So here I'm writing the microscopic action in terms of dynamical fields and sources on the two legs of the contour. So we will be interested in only in considering correlators in which we insert operators on the two legs of the contour. Okay, so why is this interesting? It's interesting because this doubling of the fields, because we have two real-time evolutions, forwards and backwards, allows us to consider both physical and stochastic fields. So the sum of the two fields is interpreted as a physical field, and the difference is interpreted as the stochastic fluctuation. We know that the underlying UV quantum field theory should be unitary. And this imposes some constraints which will play an important role on the generating functional, which are shown here. For example, when we set the sources to be equal on the two legs of the contour, or in other words, the difference to be zero, then the generating functional should be zero. And there are some reflection properties and also some positivity of the real part of W. And these all come from macroscopic unitarity. Now, in the special case of thermal states, we also have an extra condition, which comes from periodicity in imaginary time. And this is called the KMS condition, which basically says that we can translate the sources in imaginary time. And then here theta is a parameter between 0 and beta, where beta is the temperature, and then the generating functional stays the same. Okay, so having this generating functional in terms of the R and A sources, the sum and difference, can give direct access to, for example, to two-point functions and higher order point functions. For example, the retarded, advanced, and symmetric Green's function, as shown here. Okay. So this is all when we have a macroscopic theory, but now we want to move on to consider effective theories. In that case, we think of having already done some RG flow, and we want to basically write this generating functional that we had before as some effective path integral in terms of some fields phi, which are now the low energy, the relevant degrees of freedom. So, of course, the effective action in that case depends on the system that we want to consider. So how do we do this in hydrodynamics? There is a systematic procedure to write down these theories. So the first step is to identify the low energy dynamical degrees of freedom, which are relevant to the system we are considering with the symmetries, etc., and the massless modes. And then we can write down terms in the effective action in some derivative expansion, for example, if we are doing hydrodynamics. What we note in this case is that in general, phi1 and phi2, the fields on the two legs of the contour, they are coupled. And the action is in general complex, which is dual to the fact, is equivalent to the fact that we have dissipation. So after doing that, the next step is to impose the unitarity constraints that we showed before. And the reason is that the underlying theory, of course, should obey unitarity. And so we impose these constraints on the effective action now. And this is equivalent to imposing them on the generating functional. Okay, and they take the form that is shown here. This will play an important role later on. And finally, a quite non-trivial step is that we want to impose the KMS symmetry, now at the level of the effective degrees of freedom of the dynamical fields of the theory. So the way to do that was explained in some very nice papers, initially in the context of just thermal quantum field theory, and also later on in the context of hydrodynamics, which is much more involved. And this roughly corresponds to imposing a symmetry of the effective action under a kind of simultaneous KMS transformation of both the sources and the VEVs, as shown here in the slide. So maybe you are more familiar with this transformation in the classical limit, in which the stochastic fields are expanded in an H-bar expansion. And then it takes the form that is shown here. So it involves a time derivative of the physical field in the transformation of the stochastic field. This is actually very nice, because actually it can be shown that the word identities for this kind of thermal symmetry is really the fluctuation dissipation relations that we are used to from hydrodynamics. And these are supposed to be some very universal constraints and symmetries of all like thermal effective field theories. And these are very important to impose in hydrodynamic theories as well. Okay, so I now have some lightning introduction to holography, but I will be very quick because I think that most of you are familiar with that. So holography is basically a duality between some large N strongly coupled quantum field theory and some weakly coupled gravitational theory. And the generating functional of the QFT is basically identified in certain limits with the on-cell bulk axion. So we can take an ADS spacetime. Holography works very well in ADS spacetimes. And for example, if we have a scalar field in the bulk, we can solve the equations of motion, we can see how it behaves near the boundary, and the leading behavior is identified with the source of the quantum field theory and the subleading behavior with the wave of the quantum field theory. Okay, I'm going very quick, but if you have any questions, of course, you can interrupt me. So another feature of holography is that the ADS black hole thermodynamics are dual to the quantum field theory thermodynamics. And for example, the temperature of a black hole that we have in ADS is dual to the temperature of the quantum field theory. The simplest example of that is to have a Schwarzschild ADS black hole, which is shown here. And this is what we will mostly use later on as well. So in the past, there have been some real-time prescriptions for obtaining retarded Green's functions, which it's not always obvious what kind of conditions you need to impose very deep in the bulk, because you can have ingoing waves and outgoing waves. But due to physical reasons, it was argued that infall in boundary conditions, they correspond to dissipation from the quantum field theory side. Because stuff is lost, and the bulk picture is that stuff is lost in the black hole. The boundary picture is that stuff is dissipated into the environment. This was actually argued for in a more nice way later on by considering the eternal black hole diagram and identifying the two sides as the two legs of the Schwinger-Keldysh contour. Okay, and this ties very well with the fact that in general we expect horizon to encode dissipation, and an incarnation of that is that hydrodynamic transport coefficients, they are usually computed, not usually, always as far as I'm aware, from black hole horizon calculations. Okay, so I also have a dictionary here. I described some of these correspondences. Okay, the final thing that I will say is that the deep interior, as I said, of the ADS space corresponds to the UV, to the IR of the theory, and the boundary of the ADS space corresponds to the UV of the theory. Okay, so this was very quick, and let me now go and explain two different prescriptions of obtaining Schwinger-Keldysh effective actions from holography. So I will not go in historical order. This is the second one that was proposed, which is basically normal holography with a complex twist. The first step is to write down the Schwarzschild ADS in ingoing coordinates. Yeah, this is what is written in the first line there. Then Glorioso, Crossley, and Liu, they proposed a prescription which tells us to basically complexify the radial coordinate of the bulk and analytically continue around the black hole horizon. Due to the function, due to the structure of the function f here, there is a branch cut, and so GCL, they instruct us to do holography on this slightly complexified spacetime. Okay, good. This is a branch cut on the advanced Green's function. You will see it in a couple of slides. Good, okay. So if, for example, we solve, as we will do, the scalar field on this contour, there are ingoing and outgoing modes. So the outgoing modes, they will have a branch cut, as shown here. It might be obvious in a couple of slides. For convenience, actually to control this branch cut, we can define this mock tortoise coordinate, and you can immediately see that this has a branch cut there. Okay, so instead of using R, we can use this zeta coordinate. This zeta coordinate has a real value which is 0 on the upper leg, 1 on the lower leg, and the imaginary part goes from infinity to 0 on the boundary. A thing to note here is that, of course, this picture, although it looks like the Schwinger-Keldysh pictures, complex time picture that I showed before, this is in a fixed time. This is the radial radial evolution. So the 2 points at the boundaries, they are fixed time points of the Schwinger-Keldysh contour. Okay, yeah, as I said, for illustration, I will just take a complex, a massless probe scalar and do holography on this spacetime. It can be shown that the general solution on this contour takes the form shown here, where GR and GA, they are normalized at the boundary and they solve the Klein-Gordon equation as shown here. It just means that you consider this Klein-Gordon equation, but on a complex parameter. So R, here the Klein-Gordon equation has this partial R, but R is complex. This is the only thing that I mean, because R does a complex excursion around the horizon. Yeah. Sorry, R? Yeah. Okay. Okay. All I'm saying is that I'm basically solving this Klein-Gordon equation, but when okay, you can take, for example, you can parameterize this contour by a real parameter if you want. All I'm saying is that you are solving the Klein-Gordon equation on this complex. When R takes these complex values shown here. Yeah, it's fixed. Yeah. So this is a small and infinitesimal complex excursion around R8s. Okay, yeah, I'm not showing explicitly how to do that. You can see it in certain papers. Yeah, the thing to note here is that GR is the ingoing Green's function and GA is the advanced Green's function. Okay, CR and CA, they are undetermined coefficients. Okay, yeah, and sorry, also the retarded Green's function and advanced Green's function, they can be found analytically in a derivative expansion. In general, it's not you cannot solve analytically the Klein-Gordon equation. Okay, so CR and CA, basically these coefficients, they are fixed by the boundary conditions, where we impose that the bulk field takes two specific values at the two boundaries, S1 and S2. So we do find the bulk field, the full solution, and it has this specific structure. Having this bulk field, then we can put the bulk action on cell and find the generating functional of the QFT. And it can be shown that this leads to a Schwinger-Keldysh path integral. Okay, this was very quick. I didn't show any details, but yeah, the important point is to keep this in mind. And then I want to compare with another way of deriving Schwinger-Keldysh actions. Right. Yes. Not path integral. Indeed, it's what I shown here. The generating functional is equal to the bulk on cell action. Yeah, this is what I mean. The bulk on cell action with specific asymptotics. So yeah, this is what I said. Good. So let me now describe another way of doing a Schwinger-Keldysh holography, which is based on an older setup by Schwinger-Keldysh and Van Ries. So I think this makes a more intuitive sense because the previous prescription, although it's easy to use, it feels a bit more ad hoc. Schwinger-Keldysh and Van Ries instruct us to basically fill in the quantum field theory contour with some complex or mixed signature bulk. In particular, real-time segments correspond to Lorentzian pieces, and imaginary time segments correspond to Euclidean pieces. Here we can see two specific examples where we have two Euclidean evolutions, and they correspond to Euclidean pieces in the bulk, and the real-time evolution corresponds to the Lorentzian piece. The next step, basically, in this construction is that we need to impose certain matching conditions on the fixed time corners. So the places where the Euclidean and Lorentzian bulk meet, these are fixed time slices. And we want to impose that the fields and the derivative of the fields, they are continuous there. This comes basically from demanding that the full bulk action is on cell. Okay, this is a bit more complicated to use, but as has been shown, you can actually use it to derive hydrodynamic theories in a derivative expansion. The relevant state here is a thermal state for hydrodynamics, and in order to find the bulk dual of that, according to Schwinger-Keldysh and Van Ries, we need to patch together some pieces of Schwarzschild ADS. So, corresponding to the two real-time evolutions of the complex time contour, we have two Lorentzian pieces of the eternal black hole, L1 and L2, and corresponding to let me go back, corresponding to the imaginary time evolution that we have here by sigma and beta minus sigma, correspond pieces of the Sigard geometry, which is the analytic continuation of the Lorentzian black hole. So we cut open the Sigard geometry that I saw up there, and we glue together Lorentzian pieces. Then we get a space-time which kind of looks like that. This is very schematic, but I hope this is clear. So we have two Lorentzian pieces and Euclidean ones. Okay, and then we want to basically do holography on the space-time. We can, yes. Sorry, this what? Sigma, yes, okay, so I'm actually, no, it's related. So theta is an arbitrary parameter in the KMS transformation. Here I'm fixing a complex time contour, which does basically splits the imaginary time evolution in between the real-time legs. So the total imaginary time evolution is beta, it's the temperature, but I can move down the second leg by sigma. No, theta is the symmetry of the action. It's a free parameter when we impose KMS. Yeah, it does. Yeah, but I'm fixing this contour, and then theta can take any value. Indeed, it comes because of this freedom that we have. So in a sense, the freedom of having an arbitrary sigma is kind of the same freedom as doing KMS by an arbitrary theta. But yeah, I'm fixing the complex time contour, and then I will impose on it on the KMS symmetry. Okay, good. So we can write down the general form of a probe scalar, which takes roughly this form on the two Lorentzian pieces. And it takes the analytic continuation of this form on the two Euclidean pieces. Okay, so here with M, I will denote these four different pieces of the bulk spacetime. And then I impose specific matching conditions on the places where I match the bulk. So these are the matching conditions that I impose between the four pieces. I also impose that we have sources on the Lorentzian boundaries only and not on the Euclidean. So yeah, the sum of this is 0 and on the Euclidean pieces, and it's given by S1 and S2 on the Lorentzian ones. Okay, so we are just doing holography on this other spacetime. And okay, I'll not explain this in detail, but imposing the matching conditions basically gives you relations between the coefficients on the Lorentzian and Euclidean pieces. So we can show, for example, that the C1R coefficient, which is the coefficient of the retarded Green's function on the first Lorentzian piece, is equal to the coefficient of the retarded Green's function on sigma, on this other Euclidean piece. And similarly, we get other relations between the coefficients. Again, this comes from the matching conditions of Schwinger-Keldysh and Van der Waals. In the end, we can write down the full bulk solution everywhere in this bulk spacetime. Here, the first two lines are the scalar field on the Lorentzian pieces, and the other two lines, they are on the Euclidean pieces. We can actually observe that this reproduces the result that we showed earlier from the GCL condition on the two Lorentzian seats. And this agreement has also been shown for diffusive hydrodynamics up to second order derivatives. So the answers agree for the bulk field. And we can immediately see from here that if we set the two sources at the Lorentzian boundaries to be equal, then what remains is only the retarded Green's function, which corresponds to infalling boundary conditions at the horizon. And so we recover the older proposal by Son and Steinmetz. And also, yeah, a final thing to note is that this also agrees with some very recent constructions of modular flowed GCL prescription. But okay, I won't show how this works. It's just that this agrees for a general non-zero sigma. Yeah, so this paper here, it solved the equations for a Gates field in the bulk up to second order derivatives and derived the effective action for this theory. This corresponds to just a charge diffusion from the quantum field theory point of view, because a U1 gate symmetry in the bulk corresponds to a U1 global symmetry on the boundary. Good. The Schwinger-Keldysh effective actions. That. Yeah, it does. So you get the diffusive pole, but you also get the retarded advanced and symmetric functions all together because these people obtained the full effective action. Also, GCL, they did the calculations on their contour, and they obtained exactly the same action. But here, I'm just showing how this works for a bulk scalar. But this also works for a gauge field. This is what I'm saying. Good. So these are two very different geometries, and we want to understand basically why they are related, why they give the same results. The statement that we want to make, the interpretation of this agreement, is that basically this structure of the bulk solutions on the two Lorentzian sheets, it is fixed by the thermal or KMS condition that I showed in the very beginning. So in Schwinger-Keldysh van Ries, the quantum field theory contour is periodic by construction, and you fill this complex time contour with a bulk. So KMS is kind of obeyed by construction. On the other hand, in GCL, GCL involves this kind of analytic continuation around the horizon. So intuitively, it feels like it imposes KMS, but deep in the bulk. Okay, let's try to understand this a little bit better. And this is the final section of my talk. So I will use ideas from semi-holography and the membrane paradigm. This works as follows. We can think of having, I'm going back to just a single bulk now. We have just one Lorentzian black hole. We can think of separating the bulk from the horizon to the boundary in two pieces, where we put a cutoff surface. And in our calculations, we will take this cutoff surface to be really close to the horizon. In that case, the bulk action is separated into two pieces, what I call the horizon action and the UV part. And here, pi are the values of the bulk field on this cutoff surface. Why am I doing that? So intuitively, we know that the d pi r corresponds basically to the low energy dynamics of the field theory, the quantum field theory. So I kind of I want to identify this phi, the field on the membrane, as the effective field that I integrated in the very beginning of my talk when I constructed the effective action. So, yes? The bulk action is an integral from the horizon to the boundary. I'm just splitting this in two parts, from r to r plus epsilon, and r plus epsilon to the boundary. Then at the very end, when I want to put the whole bulk on cell, I need to extremize the action with respect to the value of the field on the membrane. So capital phi is the bulk field which depends on R. I am imposing basically Dirichlet boundary conditions on the cutoff surface, and then I will extremize with respect to these conditions to put the action on cell. Because I'm putting a cutoff surface there in the bulk. Okay. Yes. Is the value of this field on the cutoff? Yes. the full action will be on cell after I extremize with respect to the boundary conditions. But I'm keeping it slightly off cell. Yeah. Yeah, I agree. So I will put a phi on cell separately on like the first piece of the bulk, subject to the Dirichlet boundary conditions on the cutoff surface. And then I will not do it here in this talk, but then I want to also consider the other part of the action and minimize with respect to F. But the argument is that the low energy effective action will actually correspond to this horizon action. These constructions have also been shown to work for the more interesting case of U diffusive hydrodynamics, in which case you also need to consider to keep other massless fields, which are Wilson lines extending from the boundary to the cutoff surface, but I will not talk about this now. It's just technically more complicated, but conceptually is the same. Good. So I will focus on this low energy effective action. Just to show you a few more formulas, the membrane action takes this particular form where pi is the conjugate momentum to the field. It's like the variation of the Lagrangian with respect to R. Okay, so this is the general form of a membrane action. And here, with the risk of confusing with the quantum field theory sources, etc., yeah, we think in this action of the Dirichlet values phi as sources and pi as the conjugate momentum. If we push this cutoff surface to the boundary, we really get the sources and waves of the quantum field theory. But here I will just keep it close to the horizon. I will explain in the next slide why I'm doing that. Good. So if we solve the bulk equations of motion near the horizon, we can write the solution as a sum of ingoing and outgoing waves. So here, beta is an ingoing wave, which is regular, and there is a divergence as epsilon basically is the difference of the cutoff surface to the horizon. So the first part is the outgoing wave, which diverges on the future horizon. The reason why it takes this form is because I'm still in ingoing coordinates as GCL instructed. So from this solution, basically we can compute also the conjugate momentum. And note that in this case, we have two unknown coefficients, A and beta, A and B. And so we need two constraints in order to fully constrain the solution. One is given by the asymptotic quantum field theory source at the boundary, and the other is given by a horizon condition. So this is how Son and Starinets, they imposed infalling boundary condition at the horizon, which means that A is 0 in this expansion. You only keep the regular piece on the future horizon. This is what they did, and this is how you can derive the retarded Green's function. But here, I want to go further than that. We actually want to mimic the Schwinger-Keldysh contour, which has two pieces. And the way to, yeah, and I want to implement the Schwinger-Keldysh constraints that I showed in the beginning on this membrane action. The way to do that is basically to mimic the two Lorentzian sheets by two copies of the scalar field. So you can think of just taking two different scalar fields on a single spacetime. So, because, okay, the effective Lagrangian on the cutoff surface is really, two copies of this action that I showed earlier, with a relative minus sign because I take the time orientation to be opposite. And so in terms of RNA coordinates, it takes this form that I showed here. And then if I basically use the explicit expressions that I have in terms of A and B, but now A1, B1, A2, and B2 for the two different solutions, then I get this general form for the Lagrangian. Then I want to implement on this effective action the Schwinger-Keldysh constraints that I showed in the beginning, which are supposed to hold in any effective field theory action. And so I will impose two unitarity constraints and the dynamical KMS condition exactly as we were instructed in quantum field theory. By choosing a particular value of theta, which is beta over 2, the dynamical KMS condition basically takes the form shown here. So I will impose this symmetry on the effective on the membrane Lagrangian and the two unitarity constraints. Okay, so doing that basically gives me a solution. Okay, I will not show it in detail, but basically tells me that B1 must be equal to B2. The regular pieces of the two scalars should be equal. And A1 should be related to A2 in a particular way, as shown basically here towards the end of the slide. And this is enough to fix the form of the membrane Lagrangian, as shown here. Okay, so this is actually the main result so far. Of course, we still have two fields, phi A and phi R, the sum and difference of the two scalars, which are undetermined. These are the Dirichlet conditions on the membrane, and this will be fixed after I add to this Lagrangian the UV part, which includes the field up to the boundary and impose the boundary conditions at the true ADS boundary. But so far, this is just the dissipative part of the Schwinger-Keldysh Lagrangian. If we do an expansion in H bar, we get the form shown in the last line, which might be more familiar to people, which is also very similar to what you have in ion diffusion. But this is actually the dissipative part of model A. Yes. Okay, this is actually what we want to do next. Indeed, so GCL works also for nonlinearities in the bulk, and yeah, it will be more complicated, but the hope is that you can still apply the same constraints, because these symmetries, these constraints, the unitarity constraints and the KMS symmetries, they can be applied also, in the full nonlinear level, and they are enough to fix the action as much as it can be fixed in an effective framework. Yeah, exactly. Yeah. This also works for 3 4-point functions and endpoint correlators. Yeah, this is shown in the paper cited here. Good. Yes. Exactly, yeah. So if the bulk action had, for example, a phi to the third piece, you would have cubic terms in this effective action. But the structure of these terms, the relation between the coefficients will be fixed by KMS condition. Good. So what we want to do next, and we are working towards that, is basically to move this membrane towards the ADS boundary and really get the generating functional of the quantum field theory. And this way we will connect with the true boundary sources, the S that I had in the beginning. And we also want to show that these Schwinger-Keldysh constraints, they are preserved under this holographic RG flow. this is something plausible, but we need to show that. Doing that will basically explain what I said here at the last point, that the difference basically between these constructions is that GCL imposes KMS near the horizon, but this is enough to basically impose it along the whole RC flow up to the boundary. Yeah, but okay, we have evidence to believe that, but we still need to show that. And more generally, based on some previous work on Yuan diffusion, we expect the dissipative part of the Schwinger-Keldysh Lagrangian to take the form shown here. So GR and GA will be the retarded and advanced Green's function, which are what the bulk gives us. We need to compute them in general in a derivative expansion because we cannot analytically. But the structure of the action will be as shown. So the fact that, so I'm missing a square here. The fact that the coefficient of phi a squared is given by GR minus GA times this cotangent is basically an incarnation of the KMS symmetry. Okay, these are the expectations. And yeah, since I'm almost out of time, I will just very quickly say that the most interesting thing is to basically apply all this in other setups, so in far from equilibrium setups. So because GCL is so easy to use, basically, it has been proposed that this prescription can be extended to any dynamical horizon. So if you consider a black hole which has, for example, the Vaidia or fluid gravity form, or even wild variations beyond a derivative expansion, you can still apply GCL. No one has really done it so far, but this would be the dream. But in that case, of course, there are different notions of horizon, and it's still not clear what we want to use. So there is the event horizon, there's the apparent horizon. Maybe this holds only for isolated horizons, but we still don't know. But still, based on what I showed earlier, the hope is that this IR membrane can still be applied, so the symmetries can still be implemented there, and this will give the dissipative part of the action, even in far from equilibrium situations. So there are very interesting open questions based on that. So maybe this prescription actually defines what we mean by a local equilibrium holographic state. We have some progress which shows that basically this this implements some kind of local dynamical KMS, where the parameter, the temperature now is space-time dependent, which is non-trivial to show. And yeah, the idea is that this can be also extended to regimes where derivatives are of the order of the temperature itself. So in these quantum hydrodynamic theories. Beyond that also, we want to understand whether there's any relation to more general fluctuation dissipation relations, which hold, for example, when we have driven systems, and more general fluctuation theorems beyond near equilibrium states. Yeah, and the hope is that understanding how to implement the more general symmetries on the IR membrane will basically give us a hint as to what is the geometrization of these more general constraints, because we now see GCL as a geometrization of KMS symmetry. So other setups which might be interesting is to consider excited states by inserting operators on the Euclidean pieces of the complex time contours, which corresponds to doing perturbations on the Euclidean pieces of the bulk. And it's interesting to understand how these are related to the GCL states. And also there are many further systems in which we can do calculations. So I showed you only the dissipative part of a scalar, but it will be, of course, very interesting to consider true hydrodynamic theories with conserved charges and energy momentum. So in the bulk, we can do that by considering gauge field and metric perturbations. It's, as you said, very interesting to also consider higher point functions in the bulk and go beyond the 2-point functions that I showed here. Also, there are good reasons to suggest that we can have analytic results in low dimensions or in fluid gravity backgrounds where the derivative expansion is under control. And the very final thing, of course, is like a very ambitious goal, is to understand the relation between these two prescriptions at the level of the geometry. What I mean by that is that, and yeah, I will end with this, but these are two very different complex-looking bulks. However, we can think of complexifying both the radial direction and the time direction and consider like a very big complexified bulk. And then these two can be thought of as different cross sections of this complexified geometry. So the dream would be to understand how one can be deformed into the other, but this involves complex bulks, and this is very hard to do. Okay, I think this is all what I want to say. Thank you for your attention. Thanks. Yeah. Okay. Good. So I think the more realistic stuff is to just consider dynamical horizons. To do this, the most realistic thing is to consider dynamical horizons. This has not been done before. So we might be able to get results in far from equilibrium setups using GCL. Yeah, yeah. Or in driven states, for example, in driven systems. Yes. Yeah. Well, a lot of such structures are known again for systems, for example, for steady states. So you can have like quantum systems coupled to two different baths at different temperatures, and you can have like quantum steady states. In that cases, there are generalizations of the fluctuation dissipation relations. So this the KMS symmetry that I showed earlier is broken, but in a specific way. So the hope is that maybe we can understand how to impose these other structures on the membrane axion. If this makes sense. Yes. Depends on the system that you want to describe. So do you have like conserved charges? What do you have? Um, so um, yeah, yeah. So depending on the system that you want to describe, we'll have the corresponding bulk fields. An example of um, I mean, it's known how to do that for sorry for a bulk gauge field and metric perturbations. So, for example, if we have a conserved U1 charge on the boundary theory, this corresponds to a bulk gauge field, and basically the massless degree of freedom in the bulk are Wilson lines extending from the boundary to the cutoff surface. In the same way, for metric perturbations, so if you have energy momentum, the corresponding fields that you want to use are maps from the boundary to the horizon. They are parameterized by some function x mu, and this is dual to the fluid velocity and temperature, which are the degrees of freedom in hydrodynamics. So depending on the system that you want to describe, you need to have the corresponding fields in the bulk, if this makes sense. Here, a simple bulk scalar that I used is only relevant for model A of Halberin and Hockenberg, so near critical dynamics, relaxation dynamics. But the hope is that this uncovered some symmetry structures that will hold generally. Yes.
Yeah, here you focus on KMS. So
Yeah.
so yeah, here always discuss that. As you know, so but in principle one can start with a system.
Yes. Right.
And that's so how these translate to the function? Because PMS
Yeah.
would be
Yes.
one.
Yeah.
My question is, like, no?
Good. Yes. So Skenderis van Ries tells us how to do that. So, for example, if you have general initial states on the Schwinger-Keldysh contour, then this corresponds to specific field configurations on the fixed time slices at the end of the Lorentzian pieces. So the initial conditions that you will use on the Schwinger-Keldysh contour correspond to boundary conditions on the Lorentzian pieces. But of course, how this extends in the bulk, it's not obvious. You need to solve the bulk equation of motion. Or no.
So nothing about like the theory of how genetics
No, a general state will not have any symmetries, of course. But
like the particular, let's say Gaussian.
good. I don't know this answer. Yeah. Yeah. No, the only statement I made is that basically the GCL prescription is a geometrization of the KMS condition. And I showed that just by being agnostic, taking two Lorentzian sheets without any kind of idea of how to glue them, and then imposed the Schwinger-Keldysh symmetries. And then I derived what GCL and Keldysh van Ries derived. So it's not different at all. I'm proposing something new. Okay. Thank you very much.